All right, you guys, we'll get started. Questions? Remember how this goes? You ask questions, I answer them, then we'll stop at the end of questions. So go ahead, shoot. Anyone?
I got one thing. Alright. In the homework that's due this Thursday,
Yep.
the number 2 that's about the covalently bonded ceramics.
Mm-hmm.
For aluminum nitride?
Nitride?
Yeah. When you find the electronegativity difference, it's 1.5, right? That's what I keep getting. What would that land in? Like, would that be in, since like the ranges?
Yeah, where did you get your source for figuring out what the ranges are? So does everyone know what Shelby's talking about?
I found it online.
Oh, okay. So we're talking about the difference between covalent, polar, ionic bonds, right? And aluminum nitride is ALN or AL, yeah. So aluminum nitride, what's the electronegativity of aluminum?
1.5.
1.5. What's the electronegativity of nitrogen?
3.
3. So we can determine where aluminum nitride falls on the spectrum of covalent, polar, ionic bonds by looking at the difference in electronegativity. So the delta electronegativity equals 1.5. And so this is a tricky situation, right? If the electronegativity difference is 0, what type of bond do we have?
Non-polar. Covalent bond.
Covalent, a nice covalent, non-polar bond, right? If the electronegativity difference is 3 or 4, it's an easy call for ionic. But aluminum nitride falls sort of right in the middle. So depending on your source, electronegativity differences of 1.7 or 2.0 or ... determine the crossover between covalent or polar or ionic bonds. And so whatever your source is, just quote it and say anything with an electronegativity difference of X, I'm going to call ionic. It turns out that aluminum nitride is probably not quite different enough to be an ionic bond, so we just call it highly polar or something like that. But it's still probably in the covalent range. Your source for electronegativity difference was, what did it say for ionic bonds?
It said, for ionic bonds, it said greater than 1.5.
Oh, so it was 1.5.
Yeah, so that's why I was confused.
So it's on the border, certainly, and so you could justify it either way, but maybe saying it's just a polar bond, but it's still covalent, it's not ionic yet, is a good thing, yeah. 1.5 is a little bit low, but it'll vary depending on your source. Does everyone get that? So that was one of the examples where we didn't necessarily talk about this electronegativity difference in class, but it's something that you should have in the back of your heads. But it's really easy to spot differences between, say, sodium chloride and something like methane. You should have that in the back of your mind. It's easy to spot those ionic, polar, covalent bonds. Yeah?
So is this the so-called example calculation that you were asking for here?
Yeah, so example calculation is electronegativity of aluminum is 1.5, nitrogen is 3.0. Show me a number rather than just guessing what's what. Yeah. Good one. Okay. Other questions? Yeah.
If you have a low dielectric permittivity, does that mean your KD is high or low?
Low. Right? So KD, let's erase this so people at home can follow along. So the definition of KD is permittivity over vacuum permittivity, right? Something like that. And so this is, oh, this is dielectric. Dielectric permittivity, this is dielectric constant. And so as dielectric permittivity goes up, dielectric constant is going to go up as well, right? Does that make sense? So what is polarizability proportional to or inversely proportional to dielectric constant and dielectric permittivity? Go ahead.
Proportional.
Yep, exactly. So KD is proportional to, dielectric permittivity is proportional to alpha. Whoops, that's not a very good alpha. Alpha, polarizability. Go ahead.
Okay, so that means you're also going to have lower electronegativity, right?
Lower
If you have a
electronegativity.
high KD, you're going to have a low electronegativity and a smaller dipole.
I don't. So KD. So let's take. Is water a high KD or a low KD? High, right? What's special about water? Strong dipole, right, in water. And so we know that something that has a strong dipole, if KD is high, that means alpha is going to be high, right? So this is polarizable because of these electrons on oxygen, right? And so does water have high van der Waals forces or low van der Waals forces? High van der Waals forces, right? It's got dipole-dipole forces, and those are pretty strong, except for what's the stronger intermolecular force than dipole-dipole forces? Did I hear ionic? Is that what you guys are saying? Yeah, so ionic is the strongest, right? Covalent or Coulombic interactions are stronger than dipole-dipole, but dipole-dipole is pretty strong compared to the other ones. So, high van der Waals. Now what was the question, Taylor? You're going to have to remind me.
Well, I was checking to see, so if you have a high dielectric permittivity, that means that generally it'd be less electronegative. The molecule would have a smaller dipole moment.
So, well, so high dielectric permittivity means that you have high polarizability, right? And so polarizability, you know, it depends. If we're comparing CF4, right, versus CH4, which molecule is more polarizable out of methane or perfluoromethane here? Methane, right? Why? Well, so we know this is more polarizable. Why? Because of the electronegativity difference between CH versus FC, right? So this is a highly polar bond because fluorine is highly electronegative, right? So it holds on to those electrons. And so that pushes down the polarizability. Whereas methane, you know, both of these are nonpolar, right? But methane is more polarizable because the electronegativity difference of the C and H is less than C and F. So you really need to take it on a case-by-case basis. Look at what the molecule is. Think about more polarizable or polarizability, and then you can go back into dielectric permittivity. So water, you know, it's good to just remember that water has a high dielectric constant. And it has a high dielectric constant because it's highly polarizable. It's got these extra electrons. So really, the best thing that you can think about when you think about dielectric constant, dielectric permittivity, and polarizability is look at the molecule and decide, is it high polarizability? Is it low polarizability? Why? Why not? And that will give you a clue as to these other properties. So this relationship is really important to remember. Does that clear things up a little bit?
Yeah.
Yeah? Okay. So start with polarizability, right? That's one of the first things we talked about when we introduced van der Waals forces. So, you know, what's the polarizability of oxygen versus bromine, right? Polarizability is going to tell us a lot about the difference in van der Waals forces between these. Yes?
I'm just a little confused exactly what polarizability is. Like molecular, at the molecular level, what that means.
Yeah, so at the molecular level, you need to think about the electron. So polarizability, we're talking about how easy it is to move the electrons around the molecule. So if you draw your Lewis structure or your octet, or you think about how many electrons are around a given atom. So let's compare sodium versus potassium, right? Which atom is bigger? Potassium, right? It's farther down the table. How many electrons does potassium have? What's its number? I don't know. 19? Potassium is 12? 11? And we've got some idea that, since these are just nice symmetrical atoms, right? We've got some idea that 19, the radius for 19 electrons is going to be a lot bigger than the radius for 11 electrons, right? And so if we think about how these electrons are distributed around our molecule, we know that a bigger electron cloud, when we send in some photon of light, right? Light is a wave. It's going to shake around those electrons. And we know that 19 electrons is going to respond more to this light wave than 11 electrons are, because the 11 electrons, remember, are all attracted to the protons in the nucleus.